Okay, so we just talked about the theorem and the proof of the theorem, and now we're going to go on to page 5 of the notes, which is getting back to our original example to show how this result works and how we can use this result to prove the stability properties of the two fixed points that we found, right? So just so you remember, again, we had an f of z that looks like this, 3/4 x minus 3/4 xy plus 1/4, and then f2 is 1/2 y plus 3/4 xy. So we showed that, well, here's another table there. Okay, fix that too before I send the notes to you. Two fixed points at 1, 0 and 2/3, 1/6. So let's calculate the Jacobian. So the Jacobian is the derivative of the first function with respect to x. So 3/4 minus 3/4 y, and then that with respect to y minus 3/4 x. And then the derivative of the second function with respect to x, 3/4 y, and the second function with respect to y, 1/2 plus 3/4 x. Great. And then we have that guy right here. So that's the Jacobian that we just found. So is the fixed point at 1, 0 asymptotically stable? Oops, this should be a z. Okay, so what's the Jacobian at z star? 3/4 minus 0 minus 3/4, 0 and 1/2 plus 3/4, 3/4 minus 3/4, 0 and 5/4. So 3. Okay, what are the eigenvalues of this guy? It's upper triangular. So the eigenvalues can be read right off the diagonal. They're 3/4 and 5/4. So the spectral radius of the Jacobian at 1, 0 is 5/4, which is greater than 1, which would suggest that z star 1, 0 is unstable. And that's what we suspected by looking numerically at the plots, right? That's what it looked like. We seem to get arbitrarily far from there. Let's take a look at the next fixed point. So what's the Jacobian here? At z star is 3/4 minus 3/4 times 1/6 minus 3/4 times 2/3, 3/4 times 1/6 again, and then 1/2 plus 3/4 times 2/3. So this is 3/4 minus 1/8 minus 1/2 1/8 1/2 plus 1/2 so 6/8 minus 1/8 is 5/8 minus 1/2 1/8 1. So what are the eigenvalues? Minus this. Let's do 8 times it, right? That'll be better. So lambda minus 5 So we multiplied everything by 8, so this term became a 4, minus 4 became a positive 4, minus 1 here, and lambda minus 8. Is that right? Yeah, that looks fine. Okay, so I have lambda minus 5, lambda minus 8, minus 4, so plus 4, lambda squared, minus 13 lambda, plus 44. Is that right? That looks good. To factor it, what, 4 and 11? That's not looking promising. Okay, so lambda is 13 plus or minus the square root of 169 minus 4 times 44 all over 2. Am I not seeing a super obvious factoring? So 16, 176. Are these guys complex? Is this the time where now we go to MATLAB? Maybe. Okay. So here's when we share the screen with MATLAB because we decided that we don't want to find these eigenvalues. Okay, let's see. Share MATLAB. All right, there you go. So what are the eigenvalues of 5/8 minus 1/2, 1/8, and 1? These numbers. Great. So what's the spectral radius? We need the magnitude of these, right? And so the magnitude of a complex number can be done with abs. We'll just confirm that. If I did like 1 plus I get some number, right? That looks like it has that square root of 2 that I'm expecting to be in there, right? So it's the square root of 2. So what if I did abs of the eigenvalues here? Okay, so they're of course a complex conjugate pair. They should have the same magnitude and that number is less than 1. So let's stop sharing the screen and we'll just go back and write it down in the notes. So that is some number dot dot dot, which is like we'll write MATLAB, and that the magnitude of this 1 and 2 complex conjugate pair is something like 0.82 less than 1, which would imply that Z star, which is 2/3 and 1/6, put up here, is an asymptotically stable fixed point. Yeah, and answers in a box, which is always good for like homework and stuff. So that's it. That's all I have for today's lecture. I think it's pretty straightforward. You'll have some examples and chances to try working with this, but I think this should follow exactly from what we've seen so far with linear systems and interpreting multivariate functions. Okay, that's all. Talk to you guys on Tuesday.